We are Group 3, and today we will be presenting on analyzing supervised machine learning algorithms on banana quality and concrete compressive strength. My name is Daniel Rodarte.
I'm John Doyle.
I'm Daniel Flores.
I'm Ivan Martinez.
I'm Pilar Rodriguez.
I'm Angel Rubio.
I'm Pedro Valadez.
So in the modern day, decisions are made based off of data people have available to them. This has led to the integration of machine learning algorithms across various industries. This study analyzes the results of three fundamental machine learning algorithms: decision trees, k-nearest neighbors, and random forest regression. And these will be applied to banana quality and concrete compressive strength, respectively. In the fruit industry, quality assessment is one of, if not the most important processes in meeting consumer and supplier requirements. Classifying fruit based on factors such as size, weight, sweetness, etc. And it is necessary to measure the product quality in the agricultural sector. This is a task that can be performed through machine learning at a lower cost rather than depending on hiring a quality inspector, as that can easily cause costs to outweigh the potential benefits that they can provide. Similarly, in the construction industry, different materials like lumber and concrete depend on quality assurance to ensure that they meet industry requirements. Concrete is material used in everyday construction, from parking lots to house foundations and skyscrapers. And depending on the job type, there are different needs from the concrete used. Machine learning can be used to identify the potential fit to the job based on the factors such as water content, age, and cement composition, and classify it as such.
For this project, our first data set is based on banana quality. It was compiled by a data scientist at the Belarusian State University. So this data set is made up of 8,000 individually inspected banana reports. There are 8 total categories, with the first 7 being size, weight, sweetness, softness, harvest time, ripeness, and acidity. So these first 7 categories are all numerical and have their own respective units. And the last category is quality. So the quality category is a binary factor, as it can only state whether a banana is of good quality or bad quality. And on the next slide, there are various uses for the results of this study. So these 4 are just some of the uses that are already starting to be used in the industry. In agriculture, farmers can use the results to improve banana quality by focusing on the factors like harvest time and ripeness. In the consumer industry, consumer satisfaction can be improved by focusing on sweetness and size, as that is something that most customers look for. For the third one, by using the results on ripeness, logistics companies can optimize distribution so that they can ensure that customers receive it at the perfect ripeness. Nutritionists can use the results as an example to make recommendations to their clients, not just based on bananas, but also applying this method to other foods. Because the data can easily be broken down into categories with different class labels, we decided to apply the decision tree algorithm to this data set.
So to prepare the banana quality data, we first check the data set. To do this, we simply open the data and try to identify any unusual metrics, like an empty slot in the Excel sheet or any extremely large or small numbers. During this process, we actually didn't find any unusual numbers in the data set. So the only thing that we thought could have posed an issue was the way the categorical data was given, since it was presented as a string that declared the banana was good or bad. Luckily, we didn't have any issues with this, so prepping this data was relatively simple. So once we plugged the data into the decision tree and no errors or outrageous results were given, we continued to apply different methods. One of the methods was cross-validation split, which determines how accurate the predictive model will be by generating samples and evaluating them by comparing them with an actual model of the algorithm. In this case, we generated 5 different models. with each of their accuracy scores shown at the bottom of the code. The mean accuracy score of these 5 models was 50.4% in this case, but it is worthy to note that this value can change if the code is run again, although it shouldn't vary too much from this score, as the samples generally tend to hover around the mean accuracy score. The algorithm evaluated in this case is the decision tree, which is built by using multiple functions, one being test split. The test split function returns a group that is given a Gini index, and the closer to 0 the Gini index is, the likelihood of that root being chosen rises. This is done repeatedly until requirements are met, like the max depth, which is declared in the second line of code.
The decision tree shows the process by which the algorithm classifies a sample. Each node takes a value from a specified column from the sample and puts it into one of 2 splits until its quality can either be classified as good or bad. As you can see, the decision tree first splits the information by the banana softness at 0.8, with one node having a Gini score of 0 and the other continuing to branch off. The following node also splits the information by softness at a value of 1.75. After that, both nodes are split by sweetness. The left side of the decision tree is then separated by softness again, ending all nodes but one. The last node that needs to be split on the left side is finally split by the size of the banana at a value of 6.95. The right side of the decision tree, on the other hand, is split by the weight of the banana, for bananas that are below or equal to a value of 4.85 in softness. With this information, we can see that most bananas tend to fall into one of the 3 groups. The first group is a banana with the softness of below or equal to 0.8, which is the attribute determined by the Gini index, and the size of that group, which is shown by the sample value of 50. The second group is distinguished by a banana with the softness greater than 0.8 but smaller than 1.65 and has a value less than or equal to 4.95 in banana sweetness. The second group has the same value of 47, making it the second largest group behind the first. The final group is based on the softness of bananas being greater than 1.75 and the sweetness being above 4.85, with the sample value being 43.
Concrete compressive strength is a trait that's measured in megapascals, and it is the result of 9 different attributes. There are 1,030 varying samples in the data set that we used, each with its own composition of cement, slag, fly ash, water, superplasticizer, coarse and fine aggregate, and then time after setting that the compressive strength was tested. And that's listed in days. The next slide, we'll get into the definitions of what these are and their functions. With concrete, there are many different things that come up. Each component has its own properties and its own purposes. Cement is the primary agent in any sort of concrete. It's about 1/8 of the volume of any concrete, but this can be higher or lower depending on the purpose of the concrete. Blast furnace slag is waste from metal refinement. It's stuff you don't really want getting out in the environment, so the best solution would be to trap it in rocks, which is exactly what happens. We use blast furnace slag because it decreases cost and it increases the strength of concrete. Fly ash is another waste. It's a waste of burning coal. And when it's added to cement, it has the benefit of making the concrete much more workable in its liquid state. That means it can flow into molds easier. Superplasticizer is similar in that it's an agent that is used to make concrete flow more easily with the use of less water. Coarse and fine aggregate are the place where the concrete really gets its strength from. The aggregate it binds to itself. It's pebbles, it's sand, it's many different things. That one's probably the most important because if low quality aggregate is used, it can dissolve the rebar inside of it. So that's pretty important that you get it right. All of these things were varied, and the time after a concrete sample was poured was measured to see how these different factors could contribute to quality.
As previously mentioned, the second machine learning method we used was K nearest neighbor, also known as KNN. KNN is an algorithm that can be used for regression or classification. The basis of KNN is using nearby or neighboring data points to help predict the value of a new data point. This algorithm is preferred because it does not make any assumptions of the data and uses similarities of different data points. The first step in KNN is to split the data into testing and training sets. The training set is used to train the regression model, and the testing set is used to evaluate it. Using the k-fold cross-validation method can be used for this. The next important step is to scale your data. This step is important to ensure that all features will contribute equally. After that, the number of neighboring points being used to make the prediction is determined. It is assigned the k variable. There is no structured method to selecting the best k. The most popular method used for this is parameterizing k using a grid search. It is important to note that selecting a k value too small could lead to an overfit of data. Also, an underfit of data could be a result of a high k value. The next step in this algorithm is to calculate the distance between the new data points to all neighboring points. Once calculated, selecting the k amount of data points closest to the new data point that is trying to be predicted. The method most commonly used to calculate the distance is the Euclidean method. Now we're going to discuss how we can get results from the KNN model and how we can interpret them.
By setting k equal to 4, we obtain a mean squared error of 27% and an r-squared value of 71%. The MSE measures the average square difference between the predicted values and the actual target values. It evaluates how well the model's predictions align with the data. A lower MSE indicates the model's predictions are closer to the target values. The R-square value determines the amount of variance in the dependent variable that can be explained by the independent variables. It can range from 0 to 1 or 0% to 100%, with a higher R-squared value indicating that a larger portion of the variation in the dependent variable is accounted for by the model. For our second machine learning algorithm, we used random forest regression. We determined an MSE value of 8% and an R-squared value of 92%. Consequently, we can conclude that our second machine learning algorithm, random forest regression, outperformed the KNN algorithm. This conclusion is based on the fact that the predictor explained 92% of the variance in the outcome variable, whereas the KNN model only accounted for 71% of the variance in the outcome variable.
Using machine learning algorithms, one is able to identify information that can help predict and identify qualities of information for future use. The decision tree algorithm was able to help group and identify the qualities of bananas to acquire the wanted qualities, such as size, weight, sweetness, softness, harvest time, ripeness, acidity, and quality. The K nearest neighbor algorithm and the random forest regression were used to identify the best relationship of materials for the concrete strength. And we used the random forest regression to check the KNN algorithm and found it was more accurate than the KNN. The variables included cement, slag, fly ash, water, superplasticizer, coarse aggregate, fine aggregate, age of the sample, and compressive strength. And with these, one is able to find the relationship of the materials and the cement strength. To conclude, the machine learning algorithms used are able to help predict, identify factors of the data given for use to optimize quality and limit the need for hiring personnel.